Hi everyone. We're gonna look at some examples from section 7.6. This is the fifth time I'm trying to record this. Yesterday I went through about 50 minutes of the video and the iPad died, so the video wasn't recorded. So I'm gonna do this slightly differently. Examples 1, 2, and 3 that I've listed up to 4 here. I already have the solutions written down, and I'm just gonna go through them. And of course, I'll also send you the PDF so you can look at it. And then example 4, I'll work through in detail, and you can follow along. Okay. So here are four examples. The last one is solving an IVP, and the first three are finding the Laplace transforms of different combinations of functions with the jump function. Okay. Now the formulas that I have written here are some that we would use, of course, in conjunction with other basic formulas as well. Okay. So anyway, so let's move on to number 1 over here. The Laplace transform of t squared times u of t minus 5. Okay. So take a look. You have the Laplace transform of t squared times u of t minus 5. What can you use? Well, you can take a look. Formula 1 has powers of t multiplied by function. So maybe we could use formula 1. And then what is our function? Our function is u of t minus 5. So together with that, we need the Laplace of u of t minus 5. So formula 3. So we could use a combination of formulas 1 and 3 to find the solution to this. Alternately, if you look at formula number 4, you have a function times u of t minus a. But in our case, our function doesn't have the shift like we need to in formula 4. So maybe what we can do is try and introduce a shift. Okay. So let's look at the answers over here for this. So using 1 and 3, what do you have? We're going to make f of t be u of t minus 5 and n is 2. Okay. So what does that say? The Laplace transform of t to the n f of t is the nth derivative of the Laplace transform of f times negative 1 to the n. Okay, so we have negative 1 squared times the second derivative of the Laplace transform of u of t minus 5. Now, what is that? Formula 3 tells you that that's e to the minus 5s over s. Okay, and so we have to take the second derivative of e to the minus 5s over s, and just working through the details, we're taking a derivative with respect to s once, then a second time, take the derivative of the derivative, and it turns out to be, when you simplify everything, e to the minus 5s times 25 over s plus 10 over s squared plus 2 over s cubed. Okay? All right, now let's take a look at the second technique. The second technique we have is we're looking at the Laplace transform of t squared times u of t minus 5, where we're going to try and use the formula of Laplace transform of f of t minus a times u of t minus a. Okay, so we're going to use formula 4 from above. Okay, and what do we have? We don't have a shift in the t squared, so we're going to introduce it. So we need a t minus 5. So we put a t minus 5 plus 5 in the parentheses of the square. Okay? And then we think of t minus 5 as alpha and 5 as beta. And we use a formula for alpha plus beta whole squared. So which is alpha squared plus 2 alpha beta plus beta squared. So we have t minus 5 squared plus 5 times 2 times t minus 5. That's the second term. Plus 5 squared, which is 25, all of it times u of t minus 5. Okay, so then we have to distribute the u of t minus 5, and also let's distribute the Laplace transform, because Laplace transform of sum is sum of Laplace transforms. So you have Laplace of t minus 5 whole squared times u of t minus 5 plus, I just factored out the 10 from the Laplace, 10 times the Laplace transform of t minus 5 times u of t minus 5. plus factor out the 25, Laplace transform of u of t minus 5. Okay? And let's take a look. What is the Laplace transform of t minus 5 squared times u of t minus 5? We're just going to apply the formula. What do we need to do? What does the formula say? This is just going to be, according to the formula, the Laplace transform of the function f and multiplied by e to the minus as. Okay? So we have to put in the Laplace transform of, oh, here, I've written it right here too. Laplace transform of t squared. Okay, this is Laplace transform of t squared. And then you multiply it by e to the minus 5s. Okay? All right, second term, exactly the same way. You have Laplace transform of t, which is 1 over s squared, multiplied by e to the minus 5s. Third term, you have to just put in the Laplace transform of, maybe if you want 1 over s times e to the minus 5s, or you can just use the formula for the Laplace transform of u of t minus 5. Okay, so you can then just gather terms together and you get this. I think that this is a little bit simpler, but you know, that just whatever suits you more is fine. Okay, they both give the same answer, of course. Okay, and of course, as you're going through this video, since I've already written down the solutions for 1, 2, and 3, I would advise you to pause before you see me write down the solution, try it out yourself, and then go through the answer that I'm giving to just check your work, okay? Or just watch little bits at a time in case you're stuck. Pause as soon as you get a little unstuck, try it yourself and try and get the answer, and then watch the video to check your work. All right, so now let's go to the second one. The second one, we have the Laplace transform of sine t times u of t minus pi over 2. So here we have a function of t times u of t minus pi over 2. The only thing that I see we can easily apply is exactly, once again, this formula right here, formula number 4. So what do we need? We need a function, a shifted function multiplied by u of t minus a. Okay, so here we just have sine t. How can we write down sine t as a function evaluated at a shift? So we need to find this f such that f of t minus pi over 2 is sine t. Okay, so here's how you do it. I like to draw the unit circle, okay, and just take any angle. I mean, you can take an acute angle, that's fine. And just take a t and look at the coordinate on the unit circle. Okay, what is the sine of an angle? It's the y coordinate. The cosine is the x coordinate. Okay, so the sine of t will be this vertical length where I have marked sine t. All right? And we need to look at t minus pi over 2. So what I did is I took this angle t, okay, and subtracted pi over 2. So I came up with this dotted line over here, and this angle over here, that is sine of t minus pi over 2. So this whole thing, that is sine of t minus pi over 2. Okay? So, I mean, that's not sine of t minus pi over 2. That's t minus pi over 2. Okay, so now what do you have? You want to try and find what corresponding to this angle t minus pi over 2 gives that exact same length that we have over here in the sine of t. So take a look. Well, you know that it's going to be this length. Okay, so well, what is this length corresponding to the angle t minus pi over 2? And that is exactly the x coordinate. Okay, so you know that is the cosine of t minus pi over 2. Okay, so you know that sine t is cosine t minus pi over 2. So instead of writing sine t, we will write cosine t minus pi over 2. And now we can apply the formula where you have f of t minus a times u of t minus a. Okay, what does that say? The Laplace transform of that is e to the minus as times the Laplace transform of f of t. So it's e to the minus pi over 2s times the Laplace transform of cosine t, and that's s over s squared plus 1. Okay, 1 because it's cosine 1t. Okay, so just recall that you have the Laplace transform of cosine of bt at s. What is it? It's s over s squared plus b squared. Okay, and for sine there's a b over s squared plus b squared. Okay, so I hope this makes sense. And let's move on to the third one that we have. The third one, it is Laplace transform of e to the minus 3t. I accidentally erased that. E to the minus 3t times u of t minus 2. Okay, so what can we do? We can use the formula where you have a function times an exponential, Laplace transform of that, okay, and the function over here is u of t minus 2, and then apply the Laplace transform of u of t minus 2 to that formula that we have number 2. Okay, so the first technique we'll use formula 2 and 3 from above. I've written them down over here. Laplace transform of e to the at f of t is Laplace transform of f, but instead of evaluating at s, everywhere you see an s, you put a parenthesis and s minus a. Okay, and the Laplace transform of the f in this case is the Laplace transform of u of t minus 2. So Laplace transform of u of t minus k, we've seen as e to the minus ks over s. Okay, so let's do that. So Laplace transform of e to the minus 3t times u of t minus 2 will be the Laplace transform of t minus 2 evaluated at s minus 3. Okay, and what is the Laplace transform of u of t minus 2? That is e to the minus 2s over s. So everywhere we see an s, we'll have to put a s minus negative 3. So we'll put a s plus 3, and that's what we have is the Laplace transform of u of t minus 2. Okay? All right. And next, we're going to use the shift formula. So we're going to use formula 4, which says the Laplace transform of a shifted function times u of t minus this u at the same shift is e to the minus as times the Laplace transform of f. Okay, so what's your f? It's this exponential. We need to introduce a shift in there. So what we're going to do, we want a t minus 2 in this exponent, okay, of e. So we put a t minus 2 plus 2 right here, all right? And so essentially all we've done is, exactly all we've done is added 0 to the t, and that's obviously okay. And now we split up this exponent as e to the minus 3 times t minus 2 times e to the minus 3 times plus 2. So e to the minus 6, okay? And this is a constant. We don't need this, so we can throw this out of the Laplace transform. So what's left inside is Laplace transform of e negative 3 times t minus 2 times u of t minus 2. What does the formula say? Formula says the Laplace transform of f of t minus a times u of t minus a is e to the minus as. So it will be e to the minus 2s times the Laplace transform of e to the negative 3t, which is 1 over s minus negative 3s plus 3. So either ways, you get the same answer. Pick the technique that you like the most, but make sure that you understand both of these solutions that I've given over here for this. Okay? All right. So now that we have these basic examples worked out, let's go through problem number 4, where we're actually using the Laplace transform to find a solution to a differential equation. Okay, I've copied it down over here. Okay, so how do we solve this problem? What do we do first? Let's take the Laplace transform of both sides, and then we'll solve for the Laplace transform of z, see what its Laplace transform is, and then take inverse Laplace transform and find out what the function z is. Okay, so apply the Laplace transform. You have L of z double prime plus 3z prime plus 2z equals the Laplace transform of e to the minus 3t times u of t minus 2. Okay, the initial conditions will come into play when we're applying the Laplace transform to z prime and z double prime and so on. Okay, so the left hand side Laplace transform is linear, so you have L of z double prime plus 3 times L of z prime plus 2 times L of z and equals, what is the Laplace transform of e to the negative 3t u of t minus 2? We just looked at that in the previous problem, and that is e to the negative 6 e to the minus 2s 1 over s plus 3. Okay? All right, so coming back to this, what is this guy? It's s squared times the Laplace transform of z minus s times z of 0 minus z prime of 0. So that's the first term. Plus 3 times s times the Laplace transform of z minus z of 0. So that's the second term. Okay. Plus 2 times the Laplace transform of z, and that is e to the minus 6 e to the minus 2s times 1 over s plus 3. Okay? All right, so let's collect all the terms with the Laplace transform of z together, and all the rest will put together. So also factoring out Laplace transform of z, and what will you have? You have s squared from this one. Let me write it better. Plus 3 times s from this term right here, plus 2 from this last term. Okay? Minus s times z of 0, which is 2, so minus 2s, minus z prime of 0, which is negative 3, and then my plus 3 times, or negative 3 times z of 0 from this term. What is z of 0? You have it as 2, and that is e to the minus 6 e to the minus 2s times 1 over s plus 3. Okay? Now just do a little bit of algebra, and we have L of z times s squared plus 3s plus 2 equals e to the minus 6 e to the minus 2s over s plus 3. And what is this? This is plus 3 minus 6, so that's minus 3, so it's plus 3 plus 2s. Okay, so just taking all these terms over to the other side. All right, and so solving for L of z, of course that's a function of s. If you want, you can write that. Is e to the minus 6 e to the minus 2s times 1 over s plus 3 times 1 over s squared plus 3s plus 2 plus 3 plus 2s over s squared plus 3s plus 2. Okay, so dividing both sides with s squared plus 3s plus 2. Actually, let's not write that. It's just too much floating around as notation. Okay, so let's call this, it's just typical to call this capital Z of s, that's the Laplace transform of z, is this e to the minus 6 e to the minus 2s times 1 over s plus 3. Let me factor this one. It's s plus 2 times s plus 1. Okay, plus 3 plus 2s over s plus 2 times s plus 1. Okay, so now we're going to have to use partial fractions to rewrite these. E to the minus 6, e to the minus 2s, let's leave that alone. This will be a over s plus 3 plus b over s plus 2 plus c over s plus 1. I'm going to leave that separate from the next one as d over s plus 2 plus e over s plus 1. It's the easiest case where you have that the factors in the denominator are linear terms and distinct. Okay, and let's now find the a, b, c, d, e. So you have a 1 over s plus 3 times s plus 2 times s plus 1 equals a over s plus 3 plus b over s plus 2 plus c over s plus 1. Taking a common denominator, you have a times s plus 2 times s plus 1 plus b times s plus 3 times s plus 1 plus c times s plus 3 times s plus 2 all over s plus 3, s plus 2 times s plus 1. Equating the numerators, you get 1 equals a times s plus 2 times s plus 1. Denominators are equal. These two rational functions are equal. That means the numerators are equal. That's really what we're doing. Okay. And then you can plug in the roots of the linear terms one by one. So if you let s equals negative 3, what do we get? 1 equals a times minus 1 times minus 2 plus b times 0 plus c times 0. So that tells you that 2a is 1, so a is 1/2. You let s equals negative 2. What does that give you? 1 equals a times 0 plus b times 1 times negative 1 plus c times 0. So that tells you minus b is 1, so b is negative 1. Let s equals negative 1, and what do you get? 1 equals a times 0 plus b times 0 plus c times plus 2 times 1. So 2c is 1. So that tells you that c is 1/2. Okay? So that tells you the A, B, C. And let's find the D, E, F. And now let's find the D, E. No, sorry, not D, E, F. And what do you have? You have that second term, 3 plus 2 over s times s plus 2 times s plus 1 equals d over s plus 2 plus e over s plus 1. Taking a common denominator on the right, you have, d times s plus 1 plus e times s plus 2 over s plus 2 times s plus 1. Okay, denominators are equal, so numerators are equal, so equate that. 3 plus 2s equals d times s plus 1 plus e times s plus 2. Okay, and once again, just plug in the roots one by one. Let s equals negative 2, and what do we get? 3 plus 2 times negative 2, which is minus 1, equals d times negative 2 plus 1, that's negative 1, plus e times 0. Okay, so you get d is 1. Okay, and then you let s equals negative 1, and what do you have? 3 plus 2 times negative 1, which is 1, equals d times 0, that's gone, plus e times negative 1 plus 2, which is 1, so you get e is also 1. Okay, so that's nice. So this fractions you can rewrite with these actual numbers, and you have z of s equals e to the negative 6 e to the minus 2s times 1/2 over s plus 3 minus 1 over s plus 2 plus 1/2 over, minus 1 over s plus 2 plus 1/2 over s plus 1. Okay, plus 1 over s plus 2 plus 1 over s plus 1. Okay, the E and F, D and E terms. All right, so distribute this and you have z of s equals e to the negative 6, that's a constant, let's just leave it out. And you have 1/2 e to the minus 2s over s plus 3 minus 1 times e to the negative 2s over s plus 2 plus 1/2 times e to the negative 2s over s plus 1. Okay, I don't need to write a 1 over here. Let's just write it as a minus. Plus 1 over s plus 2 plus 1 over s plus 1. Okay, so what is the function little z of s? I'm sorry, little z of t, the solution to the differential equation. That's a Laplace inverse of capital Z of s. Okay, and so it's a Laplace inverse of this whole combination. All right, so now we need to take the Laplace inverse of this whole thing. Okay, so let's see, e to the minus 6 is a constant. Let's leave that be. How about this? 1/2 is a constant. Let's leave that be. So let's concentrate on this thing right here. What do you have? It is, if you take a look, what is that zigzaggy term? Zigzaggy term is e to the minus 2s times the Laplace transform of e to the minus 3t. Do you agree? Because what is the Laplace transform of e to the minus 3t? It's 1 over s minus negative 3. So that's 1 over s plus 3. Okay, so you have that this zigzaggy term is e to the minus 2s times Laplace transform of e to the negative 3t. Okay, what will that give you? If you remember, what's formula for above say? Laplace transform of f of t minus a times u of t minus a evaluated at s is what? E to the minus at times the Laplace transform of f at s. Sorry, not at, as. Oops, sorry. Times the Laplace transform of f at s. So that's exactly what we have. Here's the Laplace transform. 1 over s plus 3 is the Laplace transform of e to the minus 3t. You're multiplying it by e to the minus 2s. So your a is 2. F is, this is f. Okay, so the answer is f of t minus a. So e to the minus 3t evaluated at t minus a times u of t minus a. Similarly, this one is the Laplace transform of e to the minus 3t times e to the minus 2s. So it will be e to the minus, not minus 3t, minus 2t, minus 2. Instead of evaluating at t, you evaluate it at t minus 2 times u of t minus 2. Once again, the third term is 1/2 e to the minus 1t. Instead of evaluating at t, you do it at t evaluate t minus 2, and you have u of t minus 2. Okay, so these are the first terms. Okay, these guys are easy. What is 1 over s minus 2? What's the inverse Laplace of that? It is e to the minus 2t. Okay, what's the inverse Laplace of 1 over s plus 1? It is e to the minus t. Okay, so there you go. This is the solution. And if you want, you can distribute the e to the negative 6 and rewrite it, just combining the exponents any way you want. So you'll have e to the minus 3t plus 6 minus 6, so it's e to the minus 3t, u of t minus a, minus, what is this, e to the plus 4 minus 6, So e to the minus 2t minus 2, u of t minus 2. And this is plus 2 minus 6. So it is e 1/2 e to the minus t minus 4 u of t minus 2 time plus e to the minus 2t plus e to the minus t. Okay, once again, just clean up the exponents and you can write 1/2 e to the minus 3t u of t minus, not a, sorry, minus 2. 2 minus 2 minus e to the minus 2, keep that out, t plus 1, and oops, u of t minus 2 plus 1/2 e to the minus t plus 4 u of t minus 2. In fact, you know what? Sorry, I should have done this. Let's factor out a u of t minus 2. I'll just write it right here. One half e to the minus 3t. Okay. And minus e to the minus 2t plus 1. Okay. Plus 1/2 e to the minus t plus 1. Okay. And what do you have? Close that bracket, plus e to the minus 2t plus e to the minus t. That is the solution. Okay, so this function solves the initial value problem. It satisfies the differential equation and it satisfies the initial conditions. All right, well, I hope that made sense. The key to a problem like this is that when you look at it as a whole, don't jumble everything in your mind. Just do it step by step, one thing at a time. You look at, for example, Laplace transform of z prime. Okay, apply the formula for that. Apply the formula for each of the derivatives, the z. And then on the right, apply the formula on the right. You know, slowly do the algebra, gather terms together. And now you have different terms. Make sure you don't combine. For example, over here, it didn't make sense to combine the e to the minus 2s with the 1 over s plus 2, 3, 1 terms with the normal 1 over s plus 2, 1 over s plus 1 term. Why? Because when you have an exponent multiplied with the Laplace transform of something, you introduce a u. And in the plain terms, like 1 over s plus 1, 1 over s plus 2, you do not introduce a u. Okay? So I hope that made sense to you all, and that you're able to do your problems much more easily now. And also, one more thing. So, you know, it's very easy to make a small mistake in something like this and get all jumbled up and get the wrong answer. What I'm looking for really is to see if you have the big picture, if you understand what's going on. Okay, fine, maybe you made a small mistake here and there. That's okay, but I am looking to see if you've gotten the big picture and understand the main steps of what's going on and the main ideas and the main formulas that are appropriate to use over here. Okay? All right, guys. Well, take care and until next time. Bye.